Hello and welcome to this session on relational algebra and query languages. A query language takes a set of relations, let's say x, and turns them into a relation y. There are two different kinds of query languages: procedural and declarative. And of course, these form the basis, or these lay the foundation for the popular query language SQL, the structured query language. So let's get started. There are six operations that we refer to as the fundamental operations in relational algebra. Let's take a look, and hopefully the next few slides will make it evident as to why these operations are fundamental in nature. And of course, um, there are more operations which we call as extended operations. We'll look at them as well in the following course. So let's start with the select operation. Often we use notations such as these to refer to the operation. So sigma p of r denotes the select operation on r, and p is the selection predicate. So let's say we have a relation r like this, and let's say we want to select a few tuples from this relation depending on some predicate p, then we would use this operation. So here is an example. So let's say I take the instructor table and I am interested in all those tuples where the department name is physics. Then I would write something like this. The predicate department name equals physics helps me filter uh, uh, as I need. So this is what the output would be. So you have only those tuples here in the output relation where department name is physics. So I have an input relation and then I have an output relation. The next operation we look at is the project operation. Um, we use a pi to refer to that. Um, so let's say I have a instructor relation, something like this, and in this case, let's say I'm interested only in looking at the ID, name, and salary columns of the table, and want to ignore the department name. Then I would write something like this. So this projects ID, name, and salary columns from the instructor relation. One thing that you should keep in mind is that all relations are sets. So when you project certain dimensions of your tuples, it's possible that they may lead to certain duplicate tuples, and since relations are sets, we end up removing those duplicates from our um, returning relation. So here is an example. If I have the instructor table and if I drop the department name, or in other words, if I project only the ID, name, and salary columns, this is how my output would look like. Let's look at the union operation. Um, R union S is defined as all those tuples T such that T belongs to the relation R or T belongs to the relation S. Let's first look at an example. Uh, let's say we have to find all courses taught in the fall 2009 semester or in the spring 2010 semester or in both. How would I write this? So I select from section. So let's say section is the relation which carries all this information. So we select from section those tuples where semester equals fall and year equals 2009. From the resultant tuples, we project only the course ID, and then we union that with the course IDs projected from the result of this selection. So here we select all tuples from section where semester is spring and year is 2010. So the resultant course IDs are put together to get the final output, which should return all the courses taught in fall 2009 semester or in the spring 2010 semester or in both. So here is an example of a section table. So if the semester is fall and year is 2009, this is one row that could be selected for output out of this selection operation. And of course, there could be more. So there's another fall 2009 here, and there is another fall 2009 here. We could also select, so we also select semester equals spring and year 2010. So spring 2010 leads to again CS101 to be selected, and we have fin 201 and so on. And then we take the corresponding course IDs and put them together to get the output. So this should work out something like this. The set difference operation R minus S is defined as all tuples T such that T belongs to R and T does not belong to S. In other words, these tuples exist in R but they don't exist in S. So here's an example. Let's find all courses taught in the fall 2009 semester but not in the spring 2010 semester. By now you would have imagined how we would write a relational algebra expression. So we would select all fall 2009 courses and then remove spring 2010 courses from them. Yeah. Um, so we can put these together. So here is the example with the section table. So take a moment, pause this video and see what should be the output for this expression. So basically you take all fall 2009 course IDs and remove spring 2010 course IDs from them. So go ahead and work this out yourself. Okay, let's see the answer. You should get CS347 and Physics 101 as the output. Um, Now here is a quiz for you. Um, if we define R intersection S as all those tuples T such that T belongs to R and T belongs to S, then R intersection S is same as R minus S, or the difference operator is applied over here. So do you think this equality holds? Please pause the video here, think it through, and when you are ready, unpause. This happens to be true indeed, and this is an example of an extended operation. So we could describe intersection operation using um, the set difference operation. So we call certain operations as fundamental operations and certain operations as, and the other operations as extended operations. So here is a cross product, the Cartesian product operation uh, used with the notation x. So R cross S would take every row of a relation R and append every tuple of relation S along with it. So when I say append, what happens is that for this, along with this tuple, we have this entire tuple appended horizontally, and then we make a copy of the first tuple once again and then append the second tuple of the teacher's relation along with it, and so on. So let me show you how it looks. So uh, we have the first tuple from the instructor relation and the first tuple from the teacher's relation, and then the first tuple from the instructor relation along with the second tuple uh, from the teacher's relation, and so on. So all these refer to the first tuple of the instructor relation, and here are all the tuples of the second uh, as all tuples that are corresponding to the second tuple of the instructor relation, and so on. So this is what we call as a cross product or a Cartesian product. Often this kind of a Cartesian product is not useful because we lose the relationships and several unrelated data gets into the table. So often this is used as an intermediate result on which further filtering is applied. At this point, I think I should tell you a story. Um, Long time back, a French mathematician named René Descartes was sick and lying on his bed, and he was staring on the ceiling, and he saw a fly moving across the ceiling, and he wanted to explain the fly's trajectory to his friend. Um, but how would he explain it? How would he say that the fly was exactly at this position and then it moved to another position and so on? So he came up with this idea of coordinate system, and we call that now as the Cartesian coordinate system. So now you understand the idea behind the dimensions, and referring to the units of the dimensions put together as a vector and calling them as a Cartesian coordinate system. Let's say x comma y, 1 comma 1 as a bee's or a fly's position. Uh, so if you now think about it, that explains what we are doing over here. So we have two n tuples, and we are putting them together to arrive at a Cartesian product. So as I just told you, the Cartesian product instructor cross teachers associates every tuple of instructor with every tuple of teachers. We call such an operation as a join operation. So we are joining two relations. The most of the resulting rows have information about instructors who did not teach a particular course. Um, so this kind of a cross product by itself might be meaningless, but it's very useful when it comes to applying other operators on top of this and arriving at a resultant relation, which makes a lot of sense. Uh, so to get those specific tuples that we are interested in from the instructor cross teachers or the join operation, we often use some kind of filter such as this. So in this case, I filter only those tuples where the instructor ID and teacher's ID are equal. So let's go back here. So of course, I join this tuple with several tuples from the teacher's selection. But if I filter out everything that are not having the same instructor.id and teachers.id, note the way I have disambiguated the ID column with instructor.id and teachers.id. So that there's no other disambiguation required because all the other columns have different names. So I'm saved. But in this case, I had to refer to them distinctly. And if I now filter this entire relation such with the predicate that instructor ID equals teacher's ID, suddenly many columns would get filtered out. And now what I get is a meaningful relation where I know what are the courses that a particular instructor teaches. So this kind of relation is now very meaningful, and it helps me to join two uh, different relations, put them together, and infer or deduct uh, more data from them. Uh, we also have so the join that we saw right just now is called the theta join, where we join two relations RS with the predicate theta. So this is shorthand to write this. So it's other way of saying take the cross product R cross S and apply a theta predicate to it. Uh, so thus, instead of writing, take a Cartesian product of instructor cross teachers and select only those tuples with where instructor ID teachers ID matches. I could write the same thing as a join instructor and teachers table with the predicate instructor.id equals teachers.id. You should get used to this notation because this is what we would use going further from here. There are cases where the column names tell us how we want to do the join. Those kind of joins where the predicates can be avoided, in the favor of just using all common columns as the join criteria. So for example, such a join is called the natural join. So let's take this example. So if I have employee relation and a department relation, I could come up with employee join, natural join with department as follows. So what's happening over here? So for every row of employee, I take all those rows of department where the department name matches with the department name of the department table. So in this case, I would say Harry 3415 belongs to the finance department whose manager is George. So that's the output I get here. So this is what we call as a natural join. If this was a theta join, I would have mentioned that employee dot department name equals department dot department name as the predicate. But since the department name is same, I often avoid it for convenience, and if I do that, I say that I've done a natural join. One thing that you should note here is that neither the employee named Mary nor the production department appeared in the output relation. And that is because we did not have a corresponding entry on both sides of the natural join. So, for example, Mary belonged to human resources, which does not show up in the department. So, we don't worry about taking Mary to the output. On the other hand, production is headed by Charles, but there is no employee in production anyways. So you don't see them here. So we only take those employees for whom there is an entry if when we do a natural join. There is also a rename operation. It's often useful to rename certain columns before we apply a Cartesian product, and that allows us to refer to uh, um, specific columns after we perform a join. So we'll take an example to understand this. Uh, so let's say I have to find the highest salary in the university. How would I do this? So let's say the relation that I start with is this, and the objective is to find the highest salary. How would you do it? So here is a weird way of doing it. One way to do that is find all salaries that are lesser than some existing salary. I understand that this is not an intuitively straightforward way of doing it. Please be with me and try to understand how this works, and then I'll tell you why I chose such an indirect way of doing this. Um, so I take this table and ask for each salary. Is there another corresponding salary which is lesser than this salary? So for 65,000, can I find any salary that are lesser than 65,000? Um, so we have 62,000 over here. Or okay, I'm sorry. So I should say that find all salaries that are lesser than some existing salary. So when you look at that, we should get all salaries except the highest salary, which is the 95,000 salary. And now if I remove all this from all known salaries, I should get 95,000 as the result, the only salary which is left out in this step 2, and that happens to be the max salary. So let me explain what I'm trying to do here. I take instructor and do a cross product with instructor itself, right? And when I do this, I want to avoid the ambiguities of all the columns. So I just rename instructor as D, right? If I don't do this, then I have instructor dot id and instructor dot id. Now how am I going to have both of them in the output? So that's where the rename operation comes very handy. So and on top of, and once I have renamed it and put them together, then I can filter based on the predicate instructor dot salary less than d dot salary. uh, so so this would select all such tuples where the instructor has a salary which is less than at least some salary in the rest of the table. So I hope you see what's going on here. And a projection of this would give me the step to result this result. Yeah. Okay. So once again, so I take instructor relation, find the cross product with itself, and filter based on the condition that instructor dot salary is less than d dot salary. So this means that as long as there is at least one salary which is greater than the instructor's salary, such a salary will be chosen or projected as a as part of the output relation. Okay, then the only thing I need to do to arrive at the highest salary is take a projection of salary from the instructor. So I get all salaries that are there in the instructor relation and remove whatever I figured out as step 2. So this is one way to capture the highest salary in the university. So I hope now it's clear to you why we would use a rename operation. Um, Many of you might wonder, uh, is why are we doing such a convoluted way of finding the max salary? Um, so I challenge you to go ahead and figure out other ways of finding um, the max salary, provided you don't have an operator like max or a function like max. So using the existing fundamental operators, if you have to implement the function of highest or max, um, this is what you would do it. So what is relational algebra? Summarizing, relational algebra uh, allows you to express uh, your uh, intent to extract parts of the database that you are interested in. If E1 and E2 are relational algebra expressions, then we could construct more complex relational algebra expressions by using the known operators. For example, E1 union E2, that's another expression. Then I can have E1 union E2 union E3, that could be another bigger expression, and so on. So I can apply this recursively and keep constructing more and more complex relational algebra expressions. So a basic expression would be a relation in the database or just a constant relation, meaning just a single value relation. Okay, I hope the foundational ideas of relational algebra are clear. Let's now take a problem and discuss that out. Consider the following relational schema. So you have students, courses, and registration. A couple of words about schema. We refer to the structure of our relation as a schema. So if you look at it, we have three relations: students, courses, and registration. And the students relation has a roll number, which is an integer, and a student name, which is of type string. Okay, so this gives you a structure of the of the data that you have, and we call that a schema. Now the question is the following relational algebra expression equivalent to the English sentence given below? So let's first look at the English sentence, then I'll show you the relational algebra expression. Find the distinct names of all students who score more than 90% in the course numbered 107. Okay, so I read it again. Find the distinct names of all students who scored more than 90% in the course numbered 107. Okay, so before I show the expression, let me tell you that we have a courses relation. So there is a course number and we are interested in course number 107. So course number must be 107, and we are interested in all students who score more than 90% in this course, right? So the percentage information is here in the registration information. So students register for courses. So the registration information has a course number and the percent 107, and we want all such student names or student roll numbers. So in this case, distinct names is asked. So we want the name. So we go back to the students relation to get that name. So look at this. Um, so what I have done is a, natural join between registration and students. So if you do a natural join between registration and students, of course the common column is the roll number column. So it gets joined based on roll number. So now I have a way to figure out the student name who has scored more than 90% in a particular course. So that's the predicate course number equals 107 and percentage greater than 90. Now I can project only the student name from this result, and thus I could get all the distinct names whose score is more than 90% in 107 course. Convince yourself that this is correct. We'll skip this problem for now. So let me summarize. The fundamental operations are select, project, rename, set difference, Cartesian product, and union. And it's very interesting to note that these 6 operations are sufficient to express any kind of query on a relation. But as we saw in the example of finding the highest salary, um, often using these fundamental operations to come up with most of our real world uh, query needs can be quite complicated. And to avoid those complications, we introduce some extended operations which can be derived from these fundamental operations. Set intersection is one example of an extended operation that we have already seen. And assignment is another example. So let me explain what an assignment is. So let's say we have a query, find all instructors in the physics and music department. What would I do? So one way to do is to write a complex long query, but another way is to break down this expression into much simpler things like how you do in your programming stuff, let's say Python or Java. So take the instructor relation and select those tuples where the department name is physics and assign it to an intermediate relation called physics. Now think of this as a variable which you can reuse later. Similarly, I have all the music instructors, and if I'm interested in finding uh, all physics and music instructors, I could or physics or music instructors, I could simply do a physics union music here. Yeah. So even though I have to write multiple lines, this makes writing and reading the expressions much simpler. There are many other aggregate functions, and the idea here is to improve the ease of use. Here are the most common functions: the sum, max, min, average, and count. Usually we use the calligraphic G notation as shown here to use these functions. So basically what we are saying is take the relation R and sum the column C, um, and get that value out as a result. Right? So compute sum of all values of attribute C on relation R is what we are asking to do by writing this. So let me summarize. Relational algebra is very much like your normal algebra. We just use relations instead of numbers. So instead of doing 1 plus 2, we do take relation R and relation S and apply some operators there. Uh, and now that we have a way to take a relation and then or take a set of relations and then put them together and extract some part of it as output, this can be used to construct query languages. Popular query language SQL um, depends on is built on these fundamental ideas. We'll look at SQL in the future classes in more detail. So we saw three major components: the fundamental operators, the extended operations, and the aggregate functions. I hope you enjoyed this talk. See you again. Thank you.